Good morning, sir.
Yes, sir. Very good morning, madam.
Respected dignitaries, participants from the various institutions, and my dear colleagues. A very warm good morning to one and all. I, S. Reshma, Assistant Professor, Department of EEE, delighted to welcome you all on behalf of Gates Institute of Technology for the 5 days faculty development program on emerging trends and challenges in renewable energy systems organized by Department of EEE, Gates Institute of Technology, Gutti. Now I would like to request the co-convener of this program to give a brief introduction about the 5 speaker of this program. Thank you, sir.
It's my pleasure to introduce today's eminent speaker, Dr.S.Nagaraja, sir. Sir, currently working as a professor in MS Ramaiah University of Applied Science in Bengaluru. Sir has completed his PhD from JNT Kakinada. To his credit, Sir has published more than 37 international and national journals and 12 conference papers are published. Sir has published 7 book chapters. To his credit, Sir has one patent published. He has supervised one PhD students. Thank you, madam, for the given opportunity.
Now I request today's speaker.
So, madam, can you, any one of you please confirm whether my slides are visible to you or not?
Yes, sir. Visible, sir.
Yes, madam. Thank you, madam.
Okay.
So, just before starting the session, I would like to thank the management and the principal of Gates Institute of Technology, Gutti, and the head of the department and convener of this 5-day FDP program, Dr. N. Narsimhulu, sir, and co-conveners Mr. E. Ramakrishna and Mr. M. Paramesh and organizing committee for giving this opportunity to deliver a session on power converter topologies for renewable energy sources. So let us dive into the session. So here, with reference to the theme of a 5-day program on emerging trends and challenges in renewable energy sources. So here I have selected a topic on power converter topologies for renewable energy sources. So let us dive into the slides. So in the presentation outline, mainly we are going to discuss about what is renewable energy systems and what is power electronics and why the renewable energy systems are required for the power electronics. And then what here mainly we are going to discuss about the solar and wind energy conversion systems and the necessity of boost converter for renewable energy sources and what are the concept of multi-level inverter topologies and what are the different topologies of multi-level inverters and some simulation results and then conclusion. So now as we know that, here, what is renewable energy systems? So basically here the energy is derived from natural sources that are replenished at a higher rate than they are consumed. So that means once the steady state and dynamic characteristics of closed loop system. So here you can see that, this diagram, it represents the block diagram of a power electronic system. So here you can see that the heart of this system, it is the power processor. It is also called as the power controller or power converter. And here the power controller or power converter, it can make use of various semiconductor switches like thyristor, MOSFETs, BJTs, and insulated gate bipolar transistors, etc. So these are acts like as a switch And here you can see that the source, so basically the power source, it can be the AC mains, or it can be from the generators, or it can be from the batteries. But nowadays, so these sources are replaced by the renewable energy sources like solar, wind, wave, etc. So here the power controller or the power processor, so it converts the input power to which is suitable for the load. And here basically we can consider the one example, like let us assume that we need to control the speed of the DC motor as a constant. So that means, so here the load is taken as DC motor, and here if it is the load is DC motor, then probably the power converter or controller, so that can be a controlled rectifier. So here the controlled rectifier is considered as power processor. And here the sensing element also we should take it as a measurement, and that is nothing but the measurement is speed sensor. Because let us assume that we need to maintain the speed of the DC motor as a constant. In that case, the output sensor or feedback sensor, that is a speed sensor, so it will always measure the output speed of the DC motor. And let us assume that the reference speed we need to maintain as a constant at a 1500 rpm. In that case, the reference speed will be set at a 1500 rpm. And here the speed sensor always it will measure the output of the DC motor and the reference speed. Is there any deviation occurs, so then here that controller action it will give the appropriate signal to the power processor or power controller, so that the speed of the DC motor it can be maintained as constant at all the times. So here, so this is the motivation to develop the power electronic converters. So now before going to discuss about the why we need the power converters for the renewable energy sources, so let us discuss why power electronics is required. So here we have considered a simple DC to DC converter example. So let us assume that the requirement is where we need to get the 500 volts as a output is needed from the 1000 watts input. So that means, so here the input is the 1000 watts, the output requirement is it is only 500 watts. So in that case, so here we have considered the specifications as input source is 100 volts and the output load is 50 volts, 10 amperes and 500 watts. Now in this case, so the generation of the power is 1000 watts, but here the our requirement is only set at 500 watts. So that means, so here how this converter can be realized. So here probably the solution for this problem is, so normally we will use instead of the power electronic converter earlier days, it is recommended that the resistive voltage divider is used. So we know that the resistor it is a power dissipating element, so that so here the 50 volts drop is maintained at the resistor. Then the generation of the voltage is set at 100 volts. So from that we are going to deliver only the 50 volts to the output, which is as per our requirement. But the disadvantage by using this solution is, so the generation of the power is 1000 watts, but here we are going to utilize only 500 watts as per our requirement. The remaining 500 watts is getting wasted in the form of the resistance voltage divider. So that means, so this solution is not recommended because the efficiency of the system it is obviously less than or equal to 50%. And also, so the generation is 1000 watts but the utilization is only 500 watts. So that means, so but here, so we are going to dissipate that 500 watts in the form of the resistance. And in other words, in the economical point of view, we can say that, so whatever the generation, the same thing we are utilizing. That means we are going to get the electricity bill for a complete of 1000 watts though we are utilizing only 500 watts. So this solution is basically not recommended. The other solution by using the electronics is, so here you can say that, so we can use the series pass regulator, but in this case, so by maintaining the transistor which is operating at an active region, so here also we can get the 500 watts utilization, but the wastage is also here, it is 500 watts because so across the transistor, so here we are going to get the power 500 watts is getting wasted. So here also the power wasted is 500 watts because the generation of the power is 1000 watts. We are utilizing complete as per our requirement, but here also the efficiency of the system is around 50% only. So this solution is also not recommended. Now the other solution is by using the power electronic converter. So as we know that the power electronic converter, so it consists of anode terminal, cathode terminal along with the gate terminal if we are considering it as a thyristor. Okay. So now here you can say that, so with the help of the power electronic controller, so we can control the voltage as per our requirement. Now here by using the power electronic switch and by incorporating the controller, suitable controller to that particular switch, so that means, so here the switch can be operated at a only 50% duty cycle. So therefore, even though the generation of the 100 volts, we are going to utilize the 50 volts, but the amount of the voltage is not getting wasted here. So therefore, so we can make use of the power electronic control for the efficient control and conversion of the electric power. So that is the reason why we are going to use the power electronic converter here. And the other thing is, so here most of the cases, so sometimes with the use of the power electronic converter, due to the nonlinear switching characteristics behavior, so we are going to get some harmonics or ripple in the output waveform. To eliminate those harmonics and ripples, so it is suggested to use the LNC filter. So by using the filter, we can reduce the harmonics, and basically this type of the converter, it is called as the buck converter. So we know that basically the buck converter, so basically it is used to reduce the voltage as per our requirement. So here you can see that the generation of the voltage is 100 volts, but here we need to utilize only 50 volts. So therefore the switch can be operated with a 50% duty cycle, and so that we can get the output voltage as per our requirement. And here, since the use of this filter and the switch, the losses are negligible, and the efficiency it will be around more than 90% when compared to the, so here resistance voltage divider and linear pass regulator. So now as we know that the power converter means, so there are the different types of the power converters are available. So here the mainly these converters are classified into the 5 categories. So they are named as inverters, rectifiers, choppers, and cycloconverter and AC voltage controller. So here as we know that the inverter, so here basically it is used to convert the fixed DC to the fixed AC or fixed DC to the variable AC. And likewise, so here the choppers are used to convert the fixed DC to the variable DC, and rectifiers are used to convert the fixed DC to the variable AC. And whereas in the case of for the conversion of AC to AC, so here there are the two converters are available. So they are named as cycloconverters and AC voltage controllers. So here if the output frequency is not variable, so then that is called as the AC voltage controller. If the output frequency is variable, then those converters are called as cycloconverters. So that means, so for a conversion of AC to AC with a change in frequency, the cycloconverters are recommended, and for the conversion of AC to AC without change in frequency, then AC voltage controllers are recommended. So these are the converters we are going to use for any renewable energy sources. So now here, why the power electronics is required for the renewable energy sources. So as we know that the power electronics, so these are essential in integrating the various renewable energy sources and particularly the solar and wind energy systems into the power grid or independent system. So here this is basically because the power electronic converters can handle the conversion and regulation of the electric power between the variable energy sources and load or interface to the grid. So here the use of the power electronics is the power can be controlled and also the power can be converted more efficiently. So that is the reason why the power electronic converters are recommended for the renewable energy sources. And this power electronics converters, it uses the power semiconductor devices to perform the various switching action in order to achieve a conversion of the electric power. And also the power electronics, it plays a vital role of conversion and control of the electric power. So therefore the power electronic based converters are recommended for the renewable energy system. And this session is mainly deals with the solar and wind energy systems as they are most promising renewable energy sources for the generation of electric energy. So therefore, with the suitable growth of solar photovoltaic system and wind power energy system, the electric generation is expected to be more in the upcoming years. So this session is mainly deals with the concept of solar based energy systems and wind energy based renewable energy systems. So now here you can see that. So let us move into the solar energy systems. So here basically we can see that the solar energy, it is interfaced to the grid by the use of boost converter and also the three-phase multi-level inverter. So here this structure, it consists of the two power converters. One is the boost converter, the other one is three-phase multi-level inverter. So whereas in the case of the solar photovoltaic system, the DC to DC converters are used in the solar systems. In other way, we can say that the output of the solar photovoltaic panel is very less. So that means if you consider the one panel, we can get maximum of around 20 volts. So then, so we know that basically that output 20 volts which is not sufficient for any loads. So therefore it is recommended to use more number of panels which are connected in series or parallel combination to get the required amount of the output voltage as per the user requirement. But the other way is, so here we can say that if you use the more number of the solar panels which are connected in parallel or series combination, then we can say that the installation cost is also increased, and at the same time you can say that the installation area is also more. So that is the reason why, to reduce the cost of the installation cost and also the area, it is basically recommended to use the power converters, so which is called as the boost converter. So here the boost converters are used with the solar photovoltaic panel to increase the output voltage of the panel and also to match with the grid voltage levels for injecting the power into the utility grid. So here the conversion of, that means the boost converter, it is going to convert, as we know that it is DC to DC, and also the objective is we are going to increase the voltage level from the solar photovoltaic panel. For example, we can say that if the voltage of the solar panel is around 20 volts, now by using the boost converter we can increase that voltage to the 40 volts. So here, so by using that as per our requirement, so because as we know that the most residential, commercial and industrial loads, it demands the AC supply. So because that is the reason why, so here the especially the inverters are recommended to convert the DC to AC. So here, since the photovoltaic panel which is interfaced to the grid, so grid is working with the AC supply. So then we are going to interface the two converters to the solar photovoltaic panel system. So one is the boost converter, the other one is the three-phase multi-level inverter. So here, instead of using the conventional inverter, it is recommended to use the multi-level inverter, that we will discuss in the upcoming slides. So why we need the multi-level inverters. So now with this concept, so we can make sure that the solar photovoltaic panel, when it is interfaced to the grid, it uses the two power converters. One is the boost converter, the other one is the three-phase multi-level inverter. So the boost converter, it is used to increase the voltage level, and then multi-level inverter, so it is recommended to convert the DC to AC, and that will be interfaced to the grid. So now further, so wind energy systems. So here basically there are the four types of the wind energy systems are there. One is the type 1, type 2, type 3 and type 4. And the diagram which is represented here, so this is the type 4 wind energy conversion system. In this case, so we can see that, so in this setup there are three types of the generators are used. So they are named as, you can see that the first one is SCIG, that is called as the squirrel case induction generator. The other one is PMSG, permanent magnet synchronous generator, and WRSG, that is called as wound rotor synchronous generator. So these types with higher ratings can be utilized. So as the rating of the power converter should be same as the rating of the generators. And also here you can see that, so by using the higher rating of the power converters, so the size, cost and complexity of the system will increase as a result. But even though the cost of the power converter is little high, it will be only between the 7% to around 12% of the total cost of the equipment. And here you can see that there are the three types of the generators are used for the conversion of the electric power from wind energy to the grid. But here, most of the cases where it is recommended to use the permanent magnet synchronous based generator, because it is having the superior performance when compared to the squirrel case induction generator and wound rotor synchronous generator. Because the permanent magnet synchronous generator, it eliminates the slip rings, brushes, and also the design is simple when compared to the squirrel case induction generator and wound rotor synchronous generator. And here you can see that, so the gearbox is also it is used for the wind energy conversion system. However, it is optional in the case of the permanent magnet synchronous generator. So that means by using the higher rating of the permanent magnet synchronous generator, we can eliminate this gearbox. So that means, so here in the case of the PMSG, so make sure that we need to have the more pole pairs so that we can eliminate the gearbox. Now this is the wind energy conversion system which is interfaced to the grid. So here you can see that basically the wind energy system, it consists of the fluctuating wind speeds. So that is the reason why the most of the wind turbines, it generates the variable frequency alternating current. So in that reason, the power electronic converters are used to convert that variable frequency AC to the DC, and then it is converted to the fixed frequency AC when it is interfaced to the grid. So here the wind energy conversion system, if you observe, so this system basically it consists of the three power converters. They are named as diode rectifier, boost converter, and three-phase multi-level inverter. So that means the block diagram of this wind energy conversion system, which is shown in the figure, so it uses the permanent magnet synchronous generator, and along with it consists of the three power electronic converters which are named as diode rectifier, boost converter, and inverter. So if you compare the solar energy system, so this diode rectifier is not used in the solar energy conversion system, but whereas in the case of the wind energy conversion system, so it uses the three power converters by the use of diode rectifiers. So here you can see that because the generation of the permanent magnet synchronous generator is alternating in nature, so therefore to convert that AC to DC, so it is recommended to use the diode rectifier circuit. So then after that, so why it is recommended the boost converter is, so one is to increase the voltage level and also to match that voltage level with respect to the grid interfacing. And instead of the boost converter, as per our recommendation, we can also use the buck converter circuit. So we can also use the buck converter circuit. But when we are using the higher rating of the permanent magnet synchronous generators, so in that case, it is necessary to use the higher power converter. So that is the reason why the boost converter is recommended in this circuit. So here, therefore, the wind energy conversion when it is interfaced to the grid, so it is suggested to have the three power converters. So they are named as the diode rectifier, boost converter, and three-phase multi-level inverter. And here, why the pulse generator and PWM techniques are used here is, so because of this boost converter and three-phase multi-level inverter, it uses the semiconductor switches. To control that semiconductor switches, the pulse width modulation techniques are used. In other words, we can also recommend it to use the maximum power point tracking techniques for the solar energy systems and wind energy conversion systems as well. So that means, so here the proposed the PMSG based wind energy conversion system, it involves the three converters. So namely the voltage source rectifier, which is used for the conversion from AC to DC, and then boost converter, which is supplied by a permanent magnet fed rectifier, which is used to enhance or increase the voltage gain, and also the grid connected three phase multi level inverter is proposed to eliminate the power quality issues. So with the synchronization of the grid voltage and grid current, we can improve the power quality by the use of three phase multi level inverter. Now let us dive into the slides. So here the boost converter. So why the boost converter is recommended for the renewable energy sources? So here one is to enhance the voltage gain. So therefore we can use either solar photovoltaic system or wind energy conversion system in the place of input voltage VDC. So here, so this VDC is replaced by the solar photovoltaic system or wind energy system, and make sure that when we are using the wind energy conversion system, so there we should also incorporate the diode rectifier, because the generation of the wind energy conversion is alternating in nature, but the boost requirement, the input is it is required DC. So therefore the AC will be converted to the DC by the use of diode rectifier in the case of the wind energy conversion system. Now how this boost converter is going to operate is, so we know that basically when the switch is turned on, So here you can see that, so here in this mode of operation, the power switch is turned on. So therefore during the turn on operation, the DC source current flows through the inductor and therefore it is closed the circuit. And then the voltage across the capacitor that is connected to the load. And likewise, when the switch is off, so in this case, so during the turn off operation, the inductor it stores the energy and that induced current will cause the inductor's polarity to change. So therefore, so here you can see that the diode is forward biased by the inductor's polarity. So therefore, this will provide the path for the current flow through the diode and then it is connected to the load during the turn off operation. That means when the switch is in half mode, then the current is flowing through the inductor and that will be connected to the load. So now by using the KCL and KVL equation, so if you derive the formula for the voltage gain for a boost converter, then here the V naught by VDC is equivalent to the 1 by 1 minus D. So here where D is called as duty cycle. Here by controlling the duty cycle, we can get the output voltage as per our requirement. So here you can see that this figure it shows the voltage gain versus duty cycle of a boost converter, and here it is observed that the voltage gain or boost factor is quasi linear when the duty cycle is varies between the 0 to zero point 0.5. You can see that. So here when the duty cycle is varies from 0 to zero point 0.5 or 0.6, the waveform is looks like a quasi linear. So therefore, thereafter we can see that after 0.6, so here it becomes a non-linear. So that means the control of the boost converter becomes complicated after the duty cycle, the range is 0.6. So after the 0.6, the control of the duty cycle it becomes complicated due to the non-linear nature. So therefore always it is recommended to operate the boost converter within the range of 0.4 to 0.6. So within the range of 0.4 to zero point 0.6, and most of the cases it is recommended to use the duty cycle as a 0.5. So if you use the duty cycle as a 0.5, then here if you observe the corresponding voltage gain, it is equivalent to the 2. So that means whatever the input voltage it is applied by the use of the solar photovoltaic system or wind energy conversion system, the voltage is getting doubled. So therefore we can say that we are going to enhance the output voltage by the use of boost converter which is used for the renewable energy sources. Next further, so here you can see that the multi-level inverter systems. So as we discussed the solar based energy system and wind energy based energy, that means the wind energy conversion system, it is interface to the grid. For both the cases, so there the inverters plays a vital role. So therefore, so here instead of having the conventional inverters, it is recommended to use the multi-level inverters. So here the multi-level inverters, so basically it is easy to produce the high voltage and high power with one multi-level structure, and the multi-level inverters it can operate with lower switching frequency. So the advantage by operating the multi-level inverters at lower switching frequency is, so if you operate the inverter with a lower switching frequency, then the switching losses will be less. So therefore the efficiency of the system is improved. And also by increasing the number of voltage levels, so here the harmonic content of the output voltage waveform will be reduces. So that means, so by increasing the more number of voltage levels in the output waveform, So here we can get the approximate sinusoidal signal. So therefore we can improve the power quality. So that is the reason why it is also mentioned. So better spectral performance. So that means the harmonic spectrum can be improved by the use of the multi-level inverters. And also there is no electromagnetic interference problem exists here. So here there is no electromagnetic interference problem by the use of the multi-level inverters. So that is the reason why. So the multi-level inverters are recommended to use the wind energy conversion system or renewable energy systems instead of the conventional inverters. So here if you use the conventional inverters, so basically the conventional inverters, it will produces the output voltage either 0 or plus or minus VDC. They are called as two level inverters. But by the use of the two level inverters, so here we need to operate the inverters at a high switching frequency. If you operate the inverters at a high switching frequency, so then the switching losses will be more, then the efficiency of the system will be reduced. So that is the reason why to overcome this drawback, it is recommended to use the multi-level inverters. And here you can see that. So here this output voltage waveform, it represents the 11 level inverter output voltage waveform. So here you can see that. So normally the conventional inverter waveform, it will be only a square waveform. But if you use the square waveform, then the harmonic of the system, it will be very more, then efficiency of the inverter will be less. So that is the reason why always it is recommended to use the multi-level inverters for the conversion of DC to AC. Now here the some sample waveform is shown, which is having the number of levels of 11. So now here you can see that by increasing the number of levels, so this waveform, it is going to reach like as a sinusoidal waveform. So that means similarly, if you increase the 17 level or 21 level, so then your waveform, it looks like a sinusoidal signal rather than the square wave signal. So the advantage by using the more number of levels is, so since it is reaching the desired sinusoidal signal, so we can say that the harmonic performance is improved. So that means the power quality is improved by the use of the multi-level inverters. So now here you can see that the different topologies are recommended to use for a various renewable energy systems. So normally the multi-level inverter topologies are classified as conventional multi-level inverters and reduced switch multi-level inverters. And the conventional multi-level inverters are further classified as diode clamped multi-level inverter, capacitor clamped multi-level inverter, and cascaded H-bridge multi-level inverter. So let us discuss all these topologies which is applicable for the renewable energy sources. Now these are the components requirement per phase for a various multi-level inverters. So here the mainly we can concentrate with respect to the number of switching devices. So here you can see that the diode clamped multi-level inverter, it consists of the 2 into m minus 1 number of switching devices. Similarly for flying capacitor and cascaded multi-level inverter. That means the conventional multi-level inverters, so they are named as the diode clamped multi-level inverter, flying capacitor multi-level inverter, and cascaded H-bridge multi-level inverter. So these inverters requires the 2 into m minus 1 switching devices. Now let us see one by one switching topology. Here it is given, whatever it is represented in the table. Now the diode clamped multi-level inverter for M level, so it requires the M minus 1 DC bus capacitors and 2 into M minus 1 switching devices and M minus 1 into M minus 2 clamping diodes. So that means for a 3 level single phase diode clamped multi-level inverter, so for M, that means the M is equivalent to the 3 here. So therefore, the single phase 3-level diode clamped inverter topology consists of two capacitors, four switching devices, and two clamping diodes. Now here you can see that. So this is the structure of three-phase, three-level direct clamped multi-level inverter. In the previous case, the requirement of the switches or it is mentioned only for the single phase. Now it is for a three-phase means so that whatever the switching devices and clamping device diodes are considered, that will be multiplied by the 3. Now here you can see that we are using the two DC bus capacitors and then four switching devices for each phase. That means the phase A is consists of four switching devices and phase B is consists of four switching devices and phase C consists of four switching devices as well. So now here you can see that it is shared by the single voltage source which is called as VDC, and in for a renewable energy sources that VDC will be replaced by the photovoltaic system or wind energy conversion system with the use of diode rectifier. So this can be applied for a renewable energy sources by replacing that VDC with the photovoltaic system or wind energy system. Now let us discuss the operation of the three-level single-phase diode clamped inverter. So in this case, we can see that so the word VDC is shared by the two DC bus capacitors which are named as C1 and C2. So that means the VDC by 2 will be appears across the capacitor C1 and the remaining VDC by 2 will be appears across the capacitor C2. Now by turning on the upper switches like here the S11 and S12, we can get the output voltage which is appeared across the C1, that is nothing but VDC by 2. Now similarly, by turning on all the lower switches, so here you can get the output voltage as VDC by 2. Hence the load is reversed here. We are going to get the minus VDC by 2. The switching table is given for your reference. You can see that by turning on the switches S11 and S12, we are going to get the half of the voltage which is applied. So that means so here in the VDC is applied means we are going to get the VDC by 2. Similarly, if you turn on all the lower switches, so then we are going to get the minus VDC by 2. Now to get the zero output voltage, so the intermediate switches like S12 and S13 are turned on by the use of the diodes D1 and D2. So by make use of the diodes, these clamping diodes, so here we can get the output voltage as 0 because so the load is, that means your output is circulating only through the switching diodes and diodes. Therefore, we are going to get the output voltage as 0. So therefore, you can see that the output voltage waveform is shown by considering the voltage as a 200 volts. So we can get the output voltage as 0 plus VDC by 2 and minus VDC by 2. So that means we are going to generate the 3-level voltage waveform by using the diode clamped inverter. And in this case, we can say that this topology basically it cannot be recommended for a 3-level because here the waveform it looks like as a sine wave. So that is the reason why to incorporate with the renewable energy systems always it is recommended to use the higher levels. Now this is the 5-level inverter topology for a 3-phase diode clamped multi-level inverter. Now by using the formula which is given in the table, so this topology it consists of 8 switching devices per phase and 6 clamping diodes per phase, and then it requires the 4 DC bus capacitors. So that means your the output voltage VDC that is shared among the four DC bus capacitors. So they are named as C1, C2, C3, C4. So that means that each capacitor will share a common voltage of VDC by 4. So that complete voltage is divided by the number of capacitors 4. Therefore, the each capacitor will share the voltage level of VDC by 4. So now always, so it is recommended to share the common DC voltage across all the capacitors, because then only we can get the symmetrical output voltage. The symmetrical output voltage means the positive voltage, that means the positive cycle waveform, it is the replica of the negative cycle. So therefore, by maintaining the symmetrical output voltage, so we can reduce the harmonics. Now here you can see that the animation is mentioned, the how the operation takes place for a 5-level direct clamped inverter, and it is considered only a single phase topology. Now you can see that by turning on all the upper switches, that is from S1 to S4, we are going to get the output voltage. So likewise, by turning on the switches like S2, S3, S4 and S5, we are going to get the voltage at V2. Then, so that means, so here the levels are mentioned like V1, V2, V3, V4, V5. Since it is a 5 level, and we can get the level V3 by turning on the switches S3, S4, S5 and S6. Likewise, and to get the voltage of V4, so here we can turn on S4. That means from upper switch only S4 is conducted, and from the lower switches 5, 6 and 7 are conducted. Now likewise, to get the V5, all the lower switches are turned on. So basically here, by turning on the different combinations, so we can get the output voltage as 0, VDC by 2, VDC by 4 and minus VDC by 4 and minus VDC by 2. And this is the switching table which is mentioned just for your reference. However, the operation is mentioned through the animation slides. So there, by controlling the proper switching action, we can get the 5 voltage levels which are named as 0, VDC by 4, VDC by 2 and minus VDC by 4 and minus VDC by 2. And if you observe the output waveform of the 5 level inverter, we can see that the whatever the waveform appeared at the positive half cycle, the same waveform it is appeared as a replica in the negative half cycle. Therefore, this waveform it is called as a symmetrical output voltage waveform. So the idea behind that is maintaining the symmetrical output voltage is we can reduce the harmonics. So that means we can improve the power quality. Now the advantage by using the direct clamped multi-level inverter is, so when the number of levels are high enough, then here you can say that the harmonic content of that waveform it will be less. So therefore, we no need to use the filter. So here if you use the filter circuit in any conventional inverter or multi-level inverter, the disadvantage by the use of the filter is, so one is it is difficult to design, and also the controlling part is so difficult when using the filter circuit for any type of the inverter. The other disadvantage is it also increases the size. So that means the size is bulky if you use the filter circuit, and the designing of the filter circuit is also difficult. So that is the, and also cost is also more. So that is the reason why, to avoid the filter circuit, it is recommended to use the multi-level inverter. Then the other advantage is here the inverter efficiency is also more, because all the devices are switched at a fundamental switching frequency. So by the use of the multi-level inverter, we can operate the switches at a fundamental switching frequency which is equivalent to the 50 Hz. So normally the conventional inverter, it uses the more switching frequency. If you use the more switching frequency, so then harmonic content of the waveform it will be reduced, but the switching losses will be more. So therefore the efficiency of the system will be reduced. And the advantage is here, the other advantage by using the diode clamped multi-level inverter circuit is the control circuit is simple. That means the methodology to control all the switches is simple in this topology. But the disadvantage of the diode clamped multi-level inverter is it uses the excessive clamping diodes are required when the number of levels are high. So if you observe or if you check that 3 level circuit topology and 5 level the circuit topology, then by increasing the number of levels, so here the number of components is also going to increase. So that is the reason why, so here we can restrict this topology up to a maximum of 5 level. So we cannot go beyond the 5 level, which is not recommended, because it increases the complexity of the circuit by involving the more number of switching diodes and clamping diodes. So therefore, the other disadvantage is, so here you can see that the capacitor voltage is also unbalanced. So here we need to use the extra circuit to balance the capacitor voltages. As we know that, have seen that 5 level diode clamped inverter uses the 4 DC bus capacitors. So when we are using the 4 DC bus capacitor, so there here we can say that the balancing of the circuit is difficult. So that is the reason why to balance the DC bus capacitor, we need to incorporate the additional circuit. The external circuit can be recommended to balance the capacitors C1, C2, C3 and C4. So these are the disadvantages of the diode clamped multi-level inverter. So by considering these disadvantages, we can recommend this topology up to 5 levels only. Now next the other topology is capacitor clamped multi-level inverter topology. So in this case, the capacitor clamped multi-level inverter topology, so the each phase it consists of n-1 capacitors and 2 into m-1 switching devices, and also 1 by 2 times of m-1 and m-2 flying capacitors. So that means for a capacitor clamped 3 level inverter, so it requires the 2 capacitors and 4 switching devices and 1 flying capacitor. So here you can see that the structure of the capacitor clamped multi-level inverter. So as we know that, so here you can see that the VDC is also replaced by solar photovoltaic system as well as the wind energy conversion system. So that means, so here this topology also it can be recommended to use for the renewable energy systems. Here when we are using the wind energy systems, so then it is recommended to use the rectifier along with the PMSG circuit. Then the output of the rectifier will be interfaced to this multi-level inverter. So in this case, the 3-level inverter, it consists of the 2 DC bus capacitor, that is C1 and C2. So in this case, the voltage is also shared among the C1 and C2. That means whatever the voltage VDC is applied, that will be shared across C1 and C2. That means the C1 will have the voltage of VDC by 2 and C2 will have the voltage of VDC by 2. And in this case, why it is called as the capacitor clamped multi-level inverter is, so you can see that this circuit, it requires the additional capacitors, that is C1A, C1B and C1C, which is represented in the red color. So that is the reason why this is called as the capacitor clamped multi-level inverter. And it is also called as a flying capacitor multi-level inverter because of this capacitor. That means the capacitors are floated in this topology. So that is the reason why this topology is called as the capacitor clamped multi-level inverter topology or flying capacitor multi-level inverter topology. Now this is the structure of single phase 3-level capacitor clamped multi-level inverter topology, and this topology it consists of the DC bus capacitor C1 and C2, and one capacitor is floating, that is C2, and it consists of the four switching devices. So by the use of these four switching devices we are going to get the output voltages of 0, plus VDC by 2 and minus VDC by 2. And this is the topology which is shown for a 5-level inverter, and in this case also we can say that by increasing the number of levels the complexity of the circuit is going to be increased. And here also with likewise the direct clamped multi-level inverter, so here also we are going to use the four DC bus capacitors, that is C1, C2, C3 and C4, and that whatever the input voltage which is supplied by the solar photovoltaic system or wind energy conversion system, that will be shared across all the four DC bus capacitors C1, C2, C3 and C4. And the disadvantage by using this topology is now we can see that the capacitors, the requirement of the capacitors are more. And this is the configuration of 5-level single phase flying capacitor multi-level inverter. Now again by controlling the switches like S1 to S4, we can get the voltage VDC. That means so here you can get the voltage of VDC by turning on all the four switches. Then by turning on all the lower switches, we can get the minus VDC. Now similarly, we can get the output voltage of VDC by 4, VDC by 2 and 3 VDC by 4. So these are the voltage levels which we can get by the use of the various switching combinations. Therefore, our motivation is, so here we are going to get the 5 voltage levels. So the advantage by using this capacitor clamped multi-level inverter is, so it provides the switching redundancy for balancing the different voltage levels. So that means by the use of the various floating capacitors, so here the we can use the various combinations to get the more voltage levels. And also here, similar to the diode clamped multi-level inverter, by the use of the capacitor clamped multi-level inverter, so here we can reduce the harmonics. So that means we can avoid the need of the filter circuit similar to the diode clamped multi-level inverter, so that the power quality can be improved by recommending the higher number of levels. The disadvantage of this topology is, so here we need to use the more number of capacitors are required when we are increasing the number of levels. And also the inverter control, it is complicated. That means, so if you increase the levels more than 5, that is like 7 level or 9 level, then this circuit it consists of the more number of the switching devices and more number of the capacitors. So that is the reason why this topology is also suggested to use up to only 5 levels. Then the other topology, it is cascaded H-bridge multi-level inverter topology. And in this case, for a M-level inverter, it requires the 2 into M-1 switching devices, and then it also requires the M-1 2 isolated power supply, that is DC power supply. That means if you consider the single phase 3-level inverter, then this topology it consists of the 4 switching devices and 1 DC power supply. So here if you observe this topology structure for a single phase 3-level, then if you compare this topology with the diode clamped multi-level inverter and capacitor clamped multi-level inverter, we can say that So this topology here, it requires the less number of components because there is no use of the clamping diodes and there is no use of the flying capacitor. So that means this circuit, it consists of only switching devices and DC power supply. So here you can see that this is the topology for a three level inverter. It is a three phase. Since it is a three phase topology, it consists of the three modules. So three modules are connected together to become a three phase three level converter. And here the operation is also mentioned. We can say that this operation, it is similar to your single phase inverter only. It is similar to your only single phase inverter, and here we can get the output voltage as per our requirement. Here you can see that to get the output voltage VDC, just we need to turn on SA1 and SA12 dash. That means by connecting the switches in cross combination, we can get VDC and minus VDC. And here the switching states are represented for a three level cascaded H-bridge inverter, and this table it is used for a, in the voltage level is divided, that is VDC by 2 and minus VDC by 2. So that means, so basically here, so this VDC, it is going to be replaced by the renewable energy sources, that is solar based renewable energy system or wind energy system. So just then that will be interfaced to the inverter. Now here this is the cascaded H-bridge multi-level inverter topology. This is the circuit of the three phase 5-level cascaded H-bridge multi-level inverter circuit. You can consider the single phase inverter circuit, and here you can see that it consists of 8 switching devices and 2 DC sources. And the other advantage by using this cascaded H-bridge structure is, so whatever the structure it is recommended for the 3-level inverter, and to bring into the 5-level inverter, the same structure it is cascaded. That's why it is called as a cascaded multi-level inverter. Now again, if you cascade the other setup, that means the other 4 switching devices, then that structure it will become the 7-level inverter. So that means, so here you can say that just by cascading the number of the inverters, that is C1, C2, C3, C4 and VDC, then we can increase the number of levels. So the advantage by using this topology is we can increase the number of levels just by cascading the single phase 3-level structure. And when compared to the diode clamped multi-level inverter and capacitor clamped multi-level inverter, we can say that the cascaded H-bridge multi-level inverter consists of less number of components. It consists of less number of components to get the same number of voltage levels. And also here the packaging is easy when compared to the diode clamp and flying capacitor multi-level inverter, because so here the each structure is having remains same. So therefore that means the topology it is having the modular structure layout. So that is the reason why the packaging is easy, because there is no use of the additional clamping diodes and additional capacitors. And further, we can also apply the soft switching techniques to reduce the switching losses and also to reduce the device stress. So therefore, so here the waveform it can be increased to the more number of levels, and even this topology, due to these advantages, it is recommended to the higher number of levels. And the disadvantage by using this topology is it requires the separate DC sources. It requires separate DC sources. So that is the only one disadvantage which is having the cascaded H-bridge multi-level inverter when compared to the diode clamp and flying capacitor multi-level inverter. So now other thing is, so we can see that the reduced switch multi-level inverter. So here So as we discussed earlier in the classification of multi-level inverter topologies, it is classified into two types. One is the conventional multi-level inverters. The other one is reduced switch multi-level inverters. So generally the conventional multi-level inverters are recommended to use up to only 3 levels or 5 levels. But when you are increasing the more number of levels that is greater than or equal to the 7 levels, then always it is recommended to use reduced switch multi-level inverter. In the case of the reduced switch multi-level inverter, so this is the one type of the topology which is considered, which is recommended to use the renewable energy sources. So now here for a M level inverter, it consists of the 2 into M minus 1 switching devices and M minus 1 isolated power supply. It is M minus 1 by 2 it is. So now for a 7 level inverter, we can see that it consists of so 10 switching devices and 3 isolated power supplies. So here the reduced switch multi-level inverter output topology for a 7 level inverter it is shown here. So now here by increasing the number of levels, so we can get the approximate the sinusoidal waveform. So therefore we can reduce the THD. So normally here this is typo mistake. It is mentioned for a M level inverter. Basically it should be the M plus 3 switching devices. That means for any level it requires M plus 3 switching devices. If it is a 7 level, then it requires 7 plus 3, that is equivalent to the 10 switching devices. If it is a 11 level, then 11 plus 3, that is requires only 14 switching devices. And here you can see that the graphical representation it is shown. This will represent the switching comparison between the conventional multi-level inverters and reduced switch multi-level inverters. And here you can see that by increasing the number of levels, the requirement of the number of switching devices is very less in the case of the reduced switch multi-level inverter. Again, if you observe of the 5 level, when the M level is equivalent to the 5, so here the conventional multi-level inverters and reduced switch multi-level inverters requires the same number of switching devices. So that is the reason why. So when you are exceeding the number of levels more than or equivalent to 7, then the reduced switch multi-level inverters are suggested to use for the renewable energy sources. So now here you can see that the simulation results are represented for a various levels, and this will give the impact of increasing the number of levels. So that means if you increase the number of levels like 3, 5, 7, 9 and 11 etc., then the correspondingly the THD will be minimized. That means the harmonics can be reduced by increasing the number of levels. Now here it is shown the 3 level output voltage waveform, then 5 level output voltage waveform, then 7 level output voltage waveform, and then 9 level output voltage waveform. So likewise up to 11 level it is shown. So these are the simulation results. By controlling the switching devices, the respective levels are obtained, and here it is represented just to show that the variation of THD. Now you can see that the corresponding harmonic spectrum is also represented here. So this is the harmonic spectrum of the 11 level output voltage waveform, and here you can notice that what is the THD it is represented here. The THD is equivalent to the 11.18%. So that is for a 7 level output voltage, and even it is also represented the fundamental voltage that is equivalent to the 249.6. Now here you can see that the tabular column, the THD for a 3 level is it is around 53.97%. That is which is very more, and which we cannot use for a any system. So definitely if you want to use the 3 level or 5 level inverter, it is always recommended to use by the use of filter circuit. But the disadvantage by using this multi-level inverter is So instead of using the conventional inverter filter circuit, so here the rating of the filter circuit can be minimized, and also the cost is also can be reduced. Now here you can see that for a 5 level inverter output voltage, so the respective THD it is 27.44%, and for a 7 level it is around 18.47, and for a 9 level it is 13.99, that is approximately 14%, and for 11 level it is 11.18%. So that means by increasing the number of levels, your harmonic spectrum is it is reduces. That means the power quality of the waveform is improved by increasing the number of levels. Why here you can say that the power quality is improved? Because by increasing the number of levels, your the output voltage waveform it looks like a desired sinusoidal signal. So therefore, as we know that the pure sinusoidal signal it consists of the zero harmonics. That means so there is no harmonic. So for a good power quality waveform, but practically which is not possible. So as per the IEEE standards, the less than or equal to 5% THD is acceptable to use the any system. So here to get the less than or equal to the 5%, so here you can use the higher switching frequency, or else we can increase the number of levels to get the THD within the limits of as IEEE limits, or else we can also interface to the grid. So there, by using the PLL circuit, so there we can synchronize the grid voltage and grid current. So therefore we can get the THD as a less than 5%, which is applicable as per the IEEE standards. So with this, so I can conclude the session. So here, so as we discussed, so have discussed the various power converter topologies which is recommended for the renewable energy sources. So this session is mainly so gives the idea of solar photovoltaic energy systems and wind energy conversion system which is interfaced to the grid, and these are the topologies which we can recommend to use for a renewable energy sources instead of the VDC source. So if you are having any queries, so you can, these are the references, and also you can see that basically these are the except to the first reference, the remaining 2 3 4 5 6 are these are the publications which are published by myself and my co-authors. All these publications are related to the photovoltaic systems and also the wind energy conversion system and the multi-level inverters. So if you're having any queries, so you can contact me through my mail ID, that is raw11123 at the rate of gmail.com. So once again, before concluding this session, so I would like to thank the management and principal and head of the department, Dr. N. Narsimulu sir, and the co-conveners, Mr. E. Ramakrishna and Mr. Paramesh, for giving this opportunity to deliver the session on power converter topologies for renewable energy sources. So you can feel free to contact for any queries through my mail ID. Thank you.
Sir, good afternoon, sir.
Yes, sir. Good afternoon, sir.
Sir, no queries from the participants, sir.
Yes, sir.
Thank you, sir.
Yes. Thank you, sir.
Sir, thank you, sir, for your nice presentation. Now, I would like to invite convener of this program to present the vote of thanks.
Thank you, sir. On behalf of EEE Department, Gates Institute of Technology, today I take this opportunity to put all my gratitude in form of words. First of all, I would like to thank our eminent speakers, Dr. S. Senthil Kumar sir, Dr. B. Ravi Kumar sir, Dr. B. Dasagiri Reddy sir, Dr. K. Manjuna sir, Dr. S. Nagaraja Rao sir, for accepting our request, for giving such a wonderful presentation on emerging trends and challenges in renewable energy systems. And making even meaningful and interesting. Thank you very much, sir. And I would like to thank our chief guest, Professor P. Sujata Madam Garu, for accepting our request to be a chief guest for this FDP and sparing her precious time in this event. Thank you, Madam. I would like to express our proud to gratitude to our principal Madam, Dr. Sayed Surya Madam Garu, for his constant support and encouragement throughout the program. Thank you, Madam. I would like to extend my heartfelt thank to our beloved correspondent Madam, Srimati V.K. Padmavatama Madam, her encouragement throughout the FDP. Thank you, Madam. I would like to express my gratitude to our Managing Director, Sri Raghunath Reddy Sir. Thank you so much, sir, for supporting and encouraging right way. I would like to thank our Director, Madam, Srimati V.K. Srivani Madam Garu, who has initiated to this program and our continuous support right from his inspection. Thank you very much, Madam. My heartfelt thank to our co-convener E. Ramakrishna sir and Parmesh sir and the entire team S. Reshma madam, P. Malleshwar Reddy sir, Vasu sir, Rambabu sir, Chinnasunkai sir for their continuous support in making 5-day FDP program successfully completed. A big thank to Noor sir, Mechanical Department and Nagendra sir who is the backbone of this online section by providing technical support. Thank you sir. I would like to thank Monica Madam for designing flyers for this FDP program. Finally, at the end of the FDP, I would like to thank all participants of this FDP program for their glorious presence. Thank you very much.
Thank you, sir. End.